Oh, okay, there it is. Okay, I'm no longer muted, I assume. Okay, the little green bar is telling me I'm not muted. Let's see. Okay, we'll trust the green bar. Thank you for that. Okay, great. Uh, so now everyone can hear me. Okay. Um, so you can see that we get a camera, and this is a perspective camera. Um, I've definitely asked this before, but for some of the newer people, who wants to explain what the difference between a perspective and an orthographic camera is? Yes. Yeah. Kind of, yeah. So that's what that's what a perspective camera is. And then what's an orthographic camera? Oh, I get what you mean, where it's like kind of flattened. Whereas perspective is like how we would normally see things. Oh, okay, yeah, I understand. So yeah, that's pretty much it. So like basically, when you are looking at something, like I can look at that whiteboard, and that whiteboard from my perspective is about that big, right? But like obviously, I know the whiteboard is not literally this big because there's a vision cone that goes out, right? And then so things that are far apart get projected onto a smaller plane, basically, right? Whereas with an orthographic camera, this is what we use with 2D, and you can see that this is not how we see the world. This is basically what a 2D camera would be, and regardless of distance, right? Everything gets kind of flattened. So it's like what you said. It's basically an isometric view of like if you've ever played those um, like old isometric games where it's like kind of 3D, but the perspective is flattened. So it's like you don't really have any depth perception, right? So this is a difference between a perspective and an orthographic camera. So let's go ahead and start. I'm going to go into create and I'm going to create a cube. This will be my floor. I'm going to reset its transform and then we'll lower it slightly, right? So I'm looking at something that looks like this right now. And so I will go and change its size. So let's go ahead and scale it up. We're going to be kind of sloppy, but this will work. So we'll make a big plane, and this will be the ground that we'll stand on, right? And then so we have this cube. I will call it floor. And one thing that you might notice is that in 2D we have basically what's called a sprite renderer, right? Where we have a sprite and that it basically just renders the image, right? We have something here basically called a mesh renderer, right? And you can see it has a setting here for a material. And right now it just has a basic lit material here, right? And so when I click on it and I can see some settings, does anyone want to explain what a material is? You can give a good explanation of just in general, what is a material?
A material is like the kind of texture and the way graphics engines handle the texture.
Yeah, exactly. So a texture is part of a material, right? I can add I can add a texture to a material, but so that's definitely part of it. The other part of it is like kind of what you said, how the graphics engine is going to handle it. Uh, Basically, what we mean by that is how does light interact with this object, right? So, for example, if I look at any material here, right, um, you can see that light interacts with them different. This desk, for example, um, has kind of like a matte texture, right? It's not particularly shiny. Um, but it's more kind of neutral, whereas the floor has some small sort of ridges and bumps to it, right? So we can describe materials in terms of the settings we have here, right? So um, we have some basic settings here, like how metallic is it, how smooth is it. We have something called a normal map. Does anyone know what a normal map is? Yes.
It's sort of like it's like controls.
like it's like controls like height of specific like small parts of it, basically.
Yeah, exactly. So um, basically, you might imagine that, uh, for example, the ground here, this carpet is not completely smooth. It has very small um, ridges and bumps built into it, right? And what happens there is, there's a little bit of depth there, where the light is going to go and it's going to bounce off in a slightly different direction. So we're not treating it as like a completely flat object, right? So with 2D, we have some very simple settings. You basically get to pick a sprite, and you get to pick, um, and you get to pick like the color of that sprite. There are materials in 2D, we just don't use them nearly as much, right? But you can see here that um, there's some more complexity with how light is going to interact with the objects. So this is the default lit material. In order for me to make a material, I have to go here and right click, and I have to go and create, and the material. And this creates what we call like a material instance. So I already made a floor previously, but I'll make like, I guess, a floor 2, right? And so this material lives inside of your project folder like this. And any object that references that material will be referencing this asset. Which means if I change this material, I change every object that uses that material. Does that make sense? Can anyone guess why? Like, why does that make sense that we would do something like that? Versus like every object having its own material? Yes.
Because it's going to make multiple objects of the same material, and it's easier to just make them from that.
Yeah, exactly. Basically, like it's kind of wasteful to duplicate the material data for every single object, right? If every single object had to have a copy of all of this data, um, things would get out of hand slightly quickly, right? Um, so instead we say, okay, well, this object will reference this material, and so there's one material that lives in your project folder, basically. Um, okay, so I'll basically recreate kind of the material that I had before. You can see kind of like a preview of what this would look like on a circle. So I'll go for something like this, and let's make it metallic. Why not? Something like this, and then maybe a tiny bit more smooth. So then I can go into my floor object, and instead of getting my material data from this default lit material, I go and I get it from here, right? So now my game kind of looks like this. Let me go and maybe make this a little bit easier to look at. We'll make it kind of greenish, why not? Something like that. The other thing I'm going to add is basically a bunch of walls. And I'm going to do that for the very simple reason that when we're kind of moving around in 3D, it's going to be really tough to like know where we're going without a reference point. So I'm just going to copy paste some walls. These are literally just cubes that have been stretched out. So there's nothing fancy here. The art workshop is in an hour where you will learn how to actually make something look nice. But for now, we're just going to copy paste cubes. So it's just a bunch of walls. Okay. Everyone good so far? Yep. Okay. So this is kind of what our game looks like right now. And then so now I'm going to go and actually create my player. So I'm going to go and I'm going to create a capsule, right? And since I kind of want this to be a first-person game, I'm going to go ahead and delete the anything to do with drawing the mesh. So basically I'm left with a capsule collider, okay? And I'm going to go in here, and everyone see how the main camera is sort of separate from the capsule, right? This is going to be our player. What I'm going to do is take this main camera, I'm going to drag it into the player. So now this main camera is a child of the player. So I'm going to go in here, and I'm going to reset its transform. So you can see that when I go in here, this camera lives kind of right here. So I'm going to bring this up just a tiny bit, like 0.75. And then so my camera, that might be a little bit too high. We'll go 0.6. something like that. So you can see my camera kind of lives right here, right? And then so now when I move my player, right, you can see the camera moves with it, right? This is what we mean by parenting. So basically, the entire what we call the transform, so the position, the rotation, the scale of the camera is inherited from the position, rotation, scale of the from the parent object, which in this case is the player. When I say that, when I say the terms world space and local space, does that make sense to everyone? Is there anyone who wants me to explain sort of what local space is? Yes. So basically, when we're referring to the space of the scene globally, right? So like the player that doesn't have any parents, right? This is its global location, right? But when we say that, when we're looking at this, right, the camera, no matter where I move the player, right, the camera stays at the same location because this position is relative to the parent, right? So then it's in its local space, right? So you can manipulate both in code, and we'll see how to do that. But that's basically what we're talking about there. Okay. Now we're going to add some components to our player. What component should I add next if we're trying to make a player character? What's one component that should probably be on the player if we want to do things like move up, down, left, right, and jump?
Physics.
Yeah, exactly. So I'm going to go ahead and add a rigid body. And I'll do my normal rigid body settings. We did a physics workshop last semester, which y'all can check out, but basically I like to set, interpolate, and continuous on here. And this is also a good opportunity to probably explain the different axes of rotation, right? So when I say pitch, roll, and yaw, is there anyone who wants me to explain that? So if I'm looking here, which axis, if I want to pitch the player forward, which axis do I rotate around? The X, exactly. So this red axis, right? So if I rotate around the X axis, I'm pitching the player forward. So you can see here, if I go and I move this, you can see the player kind of pitches forward slightly, right? We also have something called yaw, which is the y-axis rotation, which is basically looking around laterally, right? So I can take the vertical axis and I can rotate around that. So you can imagine holding your hand up and rotating like this. This is what we call yaw, right? And this will be important when we try and get our camera movement going, right? And then finally, roll is if I'm looking at the forward axis, the z-axis, and I'm rotating around that, that's going to make the player rotate like this. Okay? So we have pitch, we have roll, we have yaw, and we have roll. Okay? So that's kind of how we're going to think of rotating the player and also the camera. Okay? In terms of the constraints I want to have on my rigid body, right? What constraints would make sense in terms of rotation? Like, do I want my player to be able to roll over? No, right? So I'm going to lock this axis. Do I want my player to fall on their face? If you get shot, maybe, yeah. But for now, in the simple case, I'll go ahead and lock this, right? What you would do there is you would either have like an animation, right? So you would play an animation and then the animation is controlling the rotation rather than the physics engine. Or what you would do is if you want it to be like physically based, you would unlock the rotation temporarily, do whatever physicsy thing you want it to do, and then relock it when you're kind of back in neutral, right? So we'll leave it like this, right? And so those are the constraints you want to have. What we'll see is that I'm actually going to directly set the rotation of the transform itself when we do camera. That's certainly not the only way to do it. It's just a very straightforward way to do it. So I'm actually going to lock all of the rotation and say that the rotation is going to be controlled by directly setting these values, right? But multiple ways to do it. This is one way. Okay. So now let's actually go and start writing some code. So I already have a kind of a player controller script, but I'll make player controller 2. So I create a new script and add this here. All right. Is there anyone here that has not seen either start or update before? Okay, so we've all seen that. That's good. So of course you're all familiar with the start is the thing that's called when the game is first loaded in. This is the first frame. This is where you do your setup code. Update is called every frame, right? So what I'm going to do is we're going to need some basic settings for our player. So I'll go serialize field, float speed, and then I'll also put a mouse sensitivity here. We don't need these right now, but sensitivity. I can spell, yay. Okay. Who wants to explain what serialize field does? Yes. Yes, exactly. What's the difference between saying serialize field and, for example, public? Yes.
With public, other scripts can access it, but serialized field is still effectively private. It just can be accessed in the editor.
Yes, exactly. So both of these can be accessed in the editor. The only difference is with public, it's accessible to every script, right? So anybody can go in and change the player speed for some reason. We typically don't want that, so we want to keep the variable private while also being able to change it in the editor. A couple of y'all mentioned that you had experience with Java but not C#. Very small quirk between the two languages. In Java, if you don't put an access modifier, so for example, if I go private float x, right? In Java, if I don't put this, what's the default? It's public. If you don't put anything in Java, it's public. C# does, in my opinion, the more reasonable thing and says if you don't put anything, it's private. So you don't have to go around and typing private everywhere like you do in Java. I have bad memories of my high school CS teachers taking off points. So okay, we will also want a reference to the camera. So we'll go camera cam, and this camera will just be camera.main. People say that doing this is expensive and you shouldn't do it repeatedly. I honestly don't even know what to believe at this point. Some people say that Unity caches this internally, and that this is entirely unnecessary and I can just go camera.main. Other people say that this will literally kill your performance. I'm pretty sure people have benchmarked it, but every time I see it benchmarked, the result is different. I just cache it. I don't ask too many questions about that. Some people say that if you do this in update, your game will run at 10 frames per second and you will be in purgatory forever. I don't know. But I do the simple thing, which is just to cache it anyway. But this is a strangely controversial thing to do. We also want to reference the rigid body so we can do all of our nice physicsy things. And this is just the component on our object, right? Do that. Okay. So the rest of this is going to go, it's going to start off very similar to, the way we would do a 2D character controller. I want WASD movement, basically. So we'll go and we'll say that move input is equal to new vector 2. And we'll go input dot get axis raw horizontal. and vertical. Okay. Before I go any further, I saw some people walk. I kind of did a little bit of a survey of people's experience before, but I saw some people walk in. Does anyone here not have any programming experience whatsoever? Okay. Everyone here knows what a vector is. Okay, great. Okay. That's good, so we can carry on. So we'll have our fixed update. And remember, our fixed update is simply the update loop we use when we want to do sort of continuous physics calculations. Fixed update runs at a fixed, the default is 50 frames per second. You can actually change that. If you, for some reason, want your physics updates to happen 200 times a second, you can do that. But the default is 50, which is usually good enough. And then so we'll say that rb.linear velocity is going to be, if we want to move this on the ground, right, we'll have a vector 3. What should this be? You can fill this in for me. Yeah. If we're looking at the x-axis of the player, right? We'll wait for that to kind of compile. So here's my player, right? Where the x-axis is the red axis, right? So this is moving left to right, right? Which means this should map to the A and D keys, right? Which is the x-axis of my move input, so that part's easy, right? The y input, the vertical axis, is just going to stay the same. So we'll go rb.linearvelocity.y. Okay. Now the z-axis, right, is my forward and back axis, right? So this is going to map to the W and S keys, which means that this is going to be move input.y. Okay. Every time I do player input, I mention this problem. What did I do wrong here? I mentioned it enough times that I should know. Yes. Do I need to do that? Because if I have this move input, I'm directly setting the velocity. If I were moving the transform directly, yeah, if I were adding to the transform, then yes.
You set it so that it moves in world space and not local space.
Well, this player controller is on the player itself, right? And the rigid body is on also the. One second. The rigid body is on the player itself, so it's going to move in world space regardless, right? Because it's not a child of anything. Does that make sense? Oh yes, we'll get to that. You're absolutely right. Yes, that's what I was looking for. What you mentioned is absolutely true. We'll do that next when we go to camera movement, but for now I just want it moving on the global axes, right? But what I was looking for is yes, I didn't normalize, right? Does anyone here want me to explain why we need to normalize these vectors, or have I kind of have I hammered in the point enough in the past? Okay. If at any point you'll need me to slow down or explain something, this is for y'all, so don't be shy at all. I'm happy to slow down at any point, but yes, exactly, we need to normalize. So we'll go, I think the syntactically easiest way to do this is probably to do something like ground velocity is equal to move input dot normalize times speed. And then here we can go ground velocity x, ground velocity y. Okay. And then so now if I set my speed to something non-zero, you can see that I should move on the global axes. But if I rotate my character slightly, like this, right, you can see I'm still moving on the global axes, like you said. So we're going to move on to camera movement next. Quick side note, one thing that's interestingly missing from the 3D rigid body as opposed to the 2D rigid body is that the 2D rigid body lets you set a gravity scale directly. You can see there's no setting for that here. I'm not a huge fan of the default gravity scale. That feels like you're on the moon. Nobody falls that slowly. So I usually like to increase the gravity scale slightly. When you're working in a 3D project, you have to change it globally. So what you have to do is you have to go to File, something like Project Settings, and then there should be a physics somewhere here. Physics, Settings, and then you can change the gravity. By default, it's what is supposed to be in real life, which is negative 9.81 meters per second. I'm going to change this to, I usually like a 2 or a 3.5x gravity scale. But that to me feels a little bit less like you're floating on Mars. But okay, so we'll go back to the player controller. And then now we need to do our camera movement, right? So we want to basically take in some movement input from our mouse. And when we look up and down, right, we want the camera to rotate up and down. But when we move left and right, when we look left and right, we want our player to actually rotate in that direction, right? So let's start with the arguably easier thing, which is just looking up and down, right? And then so hopefully you can see how we're going to kind of build this up piece by piece. So I'll go in here, and similarly to how I had a move input, I'm going to have a vector2, mouse input. And this is going to look very familiar. Or do a mouse input. This will be mouse X, mouse Y, and this will be this will be get axis. Yes. Yeah, so get axis raw will return basically one of three values, -1, 0, or 1. Get axis, on the other hand, is a sliding scale. For example, if you were to do it with your move input, what you would see is basically a very slight acceleration as you hold either one of the keys. The reason I'm doing get axis here is because I'm like 90% sure that this will make it frame rate independent. The reason I think that, I should actually look this up. The reason I think that is because I've tried it with scaling by delta time and with not scaling by delta time, and not scaling by delta time honestly looks fine. So I think under the hood, and this is consistent with what I believe a lot of other game engines do, is when you're accessing the mouse input, it will give it to you in some frame independent way. Yes?
Is this, I think this might be a Unity thing, but are just like horizontal, vertical, mouse X, mouse Y, are those like predefined variables?
Yes, and you can actually define them yourself. That would be a good thing to show how to do. So if you go into edit, I believe it's in project settings, and then, because there's a lot of different, they have their new input action system, which we're not using. It's somewhere here. I should look where this is, but if anyone knows where it is and wants to remind me, that'd be great. But it is somewhere in the project settings. You can basically define them yourself. If I wanted to create another axis, for example, by default, it's A and D and then left and right are mapped to the exact same thing. And so you can do either or. You can change that to make it only one or the other. You can add a new axis, for example, if I wanted to do, I don't know, IJKL for some reason, I can also map it to that for left-handed people. But Yes, these are also user defined, but Unity gives you some defaults that you can work with. But yeah, so we'll go in here, and then remember my first goal is to just pitch the camera up and down. So we'll keep it nice and simple to start off with, right? So I'll keep a variable here of what my current pitch is. I'll keep a float pitch. And by default, this will be 0, but I might as well be explicit about that. And what we'll basically do is we'll say that our pitch will be, we're going to add our mouse input. Or actually, I believe we're going to subtract, because an increase in the mouse input will be a decrease in the pitch, because it will be a negative x-axis rotation is this way, which is looking up. So we want we want an increase in the x to be a decrease in the pitch. So I'll go minus equals, and this will be the y input, right? And also I might as well go in here and multiply this by mouse sensitivity. You could do this at any step. You could do this either here or here. I'll just go ahead and do it all at once. But yeah, let's go in here. And for any camera transformations, I like to use late update. For the, yes. Yes. Oh, it's for, yeah, it's just a class variable. So over here, and I can also, I don't need the command line here. Does anyone know what late update does? Late update basically is just the update function that gets called after all of the other updates got called. Why would we? In my mind, there's like basically two use cases for this. At least there's two reasons I've used this. Number one is for camera movement. You want your player to have moved before the camera tries to track it. Same thing here. Here it's kind of independent because the fixed update is moving it. But basically, we want our player to have moved before we try and fiddle with the camera location, if that makes sense. Yes.
Could it help with collision too, so that you don't like run into an object after you're already looking through it?
Oh. Like with collision. So you're saying like, well, because collision is handled by the physics engine, right? So like if I put a collider on something, that collider will block it, and you don't have too much control over that. Yeah. I'm trying to think though, because if you were doing something like a check for like a raycast, that's also dependent on the physics engine, which Unity will also handle for you, right? So it's like everything will just anything sort of physics related will happen in a fixed update. But with late update, the only other case that I think it's useful for is animations. So if you're using Unity's animator and you change any property of the object, right, that will happen in update, which means if you're trying to change that same property in update through a script, the two values are going to clash and they're going to basically fight to change that same value. And you don't want that, right? So if you wanted to, for example, you want the animation to apply some transformation in update, and then you want to apply some other transformation at the same time, you can go ahead and do that in late update, and then they won't conflict with each other. So the animation will happen first, and then you can make whatever change you need to. That's occasionally useful. If you want more detail about that, let me know, but that's basically the idea. I'm curious, does anyone else use late update for something other than what I've mentioned? I knew it existed. Like, I had used Unity for like several years before I knew late update existed, to be completely honest with you. But it does come in handy sometimes. So we have this pitch. Okay, I want my cameras. So camera, I called it cam dot transform dot local Euler angles. Local Euler angles is going to be a new vector 3, and our x-axis is our pitch, and the rest will be kept at 0. Oops, I can type. Okay, so I have several questions for y'all about this. First of all, what's the deal with Euler angles? Like, what is an Euler angle? So you're right. Internally, it is a vector 4. It's called like a quaternion, which is, I mean, it is a 4-dimensional vector. This is how those rotations are expressed internally in the engine base. I mean, you can access it, right? So, for example, if I go cam.transform.rotation, you can see that this will give me back a type of quaternion, right? Which is literally, as you mentioned, it's a vector 4. It has an x, as a y, as a z, and it has a w, right? This is convenient for mathematical reasons we won't go into, but if we want to actually sort of change the x, y, and z rotation of our object, then what we would use is the Euler angles, and those are the x, y, and z. And there's some vector transformation that takes us from one to the other that Unity very conveniently does for us. Second question, why? Yes.
What was the W element for? Because there's the x, y, z transformations, but where's the fourth dimension for?
I would need to know enough about. I would need to be confident enough about quaternion math to be able to exactly answer that. But it's not like I do know that it's not exactly like a spatial representation, right? It's not like it is a 4-dimensional vector, but it's not like I guess I don't. My understanding is that you don't necessarily think of these as like existing in like I mean, all vectors exist in the space, of course, but you don't necessarily think of these sort of geometrically the way you would like your x, y, and z positions of a normal a vector is basically my understanding of that. But so that's what you get from there. But yeah, so we can directly set the pitch. And then so if I go in here, you can see if I make my, oh, mouse X is not set up. Ah, mouse X, mouse Y. And I have to go in here and we'll see. We'll figure out what kind of sensitivity is going to work. Yeah, that works. So you can see I can look up and down. If you don't want the annoying cursor, you can say something like, I think it's cursor dot lock state is equal. Oh, AI being useful for once. We'll go in here, and then so now when I click on the screen, you can see it moves around like this. You can see I don't notice too much like frame rate dependence. I'll have to look and see if GetAccess is actually doing some kind of frame rate independence. But you can also multiply this by time.delta time if you want. It won't change anything. You'll just have to scale up your mouse sensitivity. So I guess there's no reason not to multiply by time.delta time with your mouse input, but this looks perfectly fine to me. So that's that. One thing we didn't account for, which you might notice, is if I go here, I can look, like I can't do that. I can't bend over like that. What you basically have to do here is we'll go and we'll clamp the pitch. So we'll say pitch is equal to mathf.clamp. Oh wow, it knows what I want. Not exactly. Nice try. Negative 90 degrees and then like 90 degrees. Right? So that way, when I go in here, this is basically taking that range and limiting it So when oh wait, did you have a?
Yeah, sorry. I'm not seeing
Oh,
my
you're
phone. So I guess this might be a C# thing. I would have
Yes.
thought to put like an if statement instead, but you like redefined pitch there.
Yes.
Is that just like a more efficient like processing way of doing it, or
It's I guess a more concise way of doing it. We totally could have done what you're saying. That is what clamp will do. Um,
oh like internally?
yeah, like this is clamped. So it is just adding the if statement.
Okay.
Yeah. Um, as for what's more efficient, um, that is kind of more so up to what the C# runtime and what the compiler wants to do with it. There's many layers that take us from like the code you're seeing here to the code that's actually running on your machine. And compilers will do all sorts of crazy things to kind of optimize and so those kind of like those things are sometimes worth worrying about, but in this case, it won't make really any difference. Um, but yeah, internally it is doing exactly what you said. Um, but yeah, so we can look up and down. Now we want to look left and right. So for looking left and right, I'm going to do a very similar thing. Before I move on, does anyone have any questions about what we've done? All right, so we're going to now start to look around, right? And I'm going to do a very similar thing. So our yaw is going to be increased by mouse input dot x, right? And we kind of want this to, we don't want it to kind of go off into infinity. We want to keep this from 0 to 360, right? So easiest way to do that is to go mod equals 360, right? Does everyone understand why does anyone want me to explain why we do this? So if we ever leave the 360 range, so if we're 361, then it'll go back to 1, right? Conversely, if we go -1, we'll go back up to 360, right? So that's our yaw. And then here we can go transform dot Euler angle. So in this case, there's no need to say local because we're dealing with the player itself. So we'll go here and we'll make this vector 3. And then remember that the yaw goes with the y. So it'll go in here. And then just to be extra clear that these are floats, go in here. And then hopefully we should have a character that can look around. So you can see I can go here and I can do all of the sort of first person looking around things. But we haven't fixed what you had brought up before, which is if I'm looking this way and I hold W, I want to move in that direction, but I'm moving along the global axes, right? Does anyone have any ideas of how we can deal with that? Yes.
You can take that vector you put in philosophy,
Yes.
you can normalize it, and then multiply it. You multiply it. Oh,
You're on the right track. You're definitely on the right track. I guess I'll try and maybe help out a bit. Let's see here. So right now, what you can basically think of us doing is, right? Basically think of us doing, and you might be able to sort of come to this conclusion without doing all of this extra math. And I think it's worth going into the, I guess, slightly unnecessary amounts of detail, because when you encounter situations that are more complex, you'll kind of have this slightly more abstract understanding. You can think of, so our velocity right here is you have some x and y velocity, right? What we're basically saying is that we're going to combine these vectors, right? And this is going to move along the x-axis, and this is going to move along the y-axis, right? I guess I should be better about my notation terms. And then so you can think of this coordinate plane as being defined by a couple of, for all of the freshman CS majors who are in the knowledge, this might sound very suspiciously familiar. You can think of this coordinate plane that we have here as being like defined by these two, what we call basis vectors, in the sense that they kind of, together they can describe any vector in this space, right? We call this, the x-axis here is, I think, by convention called I, and then this one here would be called j. So another way of describing this vector is as I times x plus j times y, right? Where j is this unit vector of 1, 0, and j is 0, 1, right? So this is one way of thinking of it, right? What you're basically saying is we want to change these basis vectors such that we're kind of rotated along in wherever we're facing, right? So like, so here, if I'm facing this direction, then this is the basis, but then if I rotate, then instead of this basis, we want maybe something like this, right? And then so we want our velocity to instead describe a point that's been kind of transformed in this way, which instead of being I times j, it's like whatever my forward vector is times my right vector, right? So you can think of this as being like the unit vector. When I say unit vector, does that make sense to everyone? Yeah. The unit vector that kind of points forward, and the unit vector that kind of points perpendicularly to my right, right? So instead of combining these like this, we'll get our ground velocity by sort of multiplying out this forward vector, this right vector, and some of these. Does that kind of make sense? Right. So the only thing we need to do is find our forward vector and find our right vector. So I'm not sure if y'all are ready for this level of incredible math here. We're going to go transform dot forward. And then we'll have, and then so this will be our, so instead of move input, we'll have transform dot forward times our move input dot x plus y'all are not ready for this, transform dot right times move input dot y. Unity is very nice. It does a lot of these sort of basic transformations for you, so you just kind of have to know how to use them. We don't have to go in through all the fancy the fancy matrix transformations about how to do any of this. We just have to kind of know what the symbols mean, right? So we'll have our transform dot forward times our move input dot x, transform dot right times our move input dot y, right? So we've basically transformed this move input into this new coordinate space, and then we're going to normalize all of that, right? And then we're going to multiply by speed, right? And then that will be our ground velocity, right? What I mean by normalize is, yes, exactly. So if I have a vector, oh, a couple minutes up. But this will be sort of the last thing we do. If I have a vector, so if I describe some vector as x and y, right? Let's say I have vector 1, 1, right? And then so you can kind of think of this as like an arrow.
I get what you mean now, like in like stats and properly. Okay.
Yeah, or I mean, the interpretation of an arrow is kind of a very physicsy interpretation. But you're right. It's really just two numbers. But if you do think about this as like an arrow where we go over 1, up by 1, and then we have sort of this vector right here. So this is a vector that we're interested in. What would the length of this vector be? Yeah, simply by Pythagorean rule. So what we mean by normalize is take this same vector, keep the same direction, but make the length of it 1, right? So what would that look like? It would look like just dividing by the length. So this would become 1 over square root of 2, 1 over square root of 2, right? The reason we have to do that is because if we didn't do that, then when I move diagonally, my velocity vector is now scaled by square root of 2 instead of by 1. And square root of 2 is approximately 1.4. So I'm actually moving 40% faster on the diagonal axis if I don't normalize this. So that's the reason why we sort of divide by the length of that vector, so that no matter which direction I'm facing, that vector has a length of 1, so our velocity is scaled by a constant value, basically. So that's the idea of the normalizing. So this is a very long line, but to kind of break it down again in a way that's hopefully easy to see, we have, it's the easiest way for me to show this. So we have our x component, which is multiplied by transform.forward. We have our y component, which is multiplied by transform.right. And then we normalize all of that to keep it at a unit length. And then we scale that back to speed. Okay? So now, when I go back, what we should hopefully see is that when we look around, I'm moving, maybe not in the way that I wanted to. Oh, transform.right, .move input dot. Oh, I screwed this up. Right. It should be y because y is our forward, x is our lateral. So sorry about that. That's slightly strange. Anyone have any ideas? I'm very quickly out of time. I will post in the Discord what is wrong with this. The what? That shouldn't matter because this is being transformed this way. I'm out of time. I will figure out what is wrong with this, and then I will post it in the Discord, assuming you're in the Discord. But basically, that's the idea: is you want to transform it like this. But we have an art workshop now, so I will go ahead and switch this up.